Hey guys, and welcome to another session in the Mind Grid. Today we are talking about CRC32 at high speed design using either tables or functions, and we want to see how these two methods are similar in many ways and are being used in the industry quite a lot for hardware design. CRC is at very high speeds in high speed chips. These kind of approaches would be used. So let's delve into how these are accomplished at those high speeds. So before we begin, I guess I just wanted to talk to you about variety of CRC based approaches that I have published over the years on YouTube. You can see that in 2020 I started working on this table based CRC approaches, and I have done 100 gig CRC back then. I have done various other CRC parallel computation introductions over time. So there's a lot of CRC tutorials on my channel. This tutorial is kind of a recap since I've been working on it for the last 5-6 years. I want to kind of recap it and show you what I've learned over these years. Actually, I've worked on CRCs for more than 10 years, but in the last 5 years, I have seen multiple approaches evolve, and people apply different types of approaches to accomplish the same thing, except the differences might be subtle, like, how many gates you're utilizing, certain kinds of memories you have in your hardware, and so on and so forth. So there's different trade-offs, but you can see that all of these things are possible, and you can make a choice according to your design. So now that being said, just a basic premise of CRC, you will see this everywhere, is that CRC itself is just a division algorithm. CRC is a remainder, right? So we all know that CRC is just a remainder, but the message is being passed in as the quotient, or sorry, the number, and then the divisor is your polynomial, right? And so this is really all there is to it. And I'll tell you the subtle difference is that if you were to just do a simple division in math and just stick the remainder at the bottom as your CRC, you won't be wrong. But the way traditional CRC is computed, it is computed over something called as a Galois field, a binary Galois field, right? And instead of using real division math, we use what is called as XOR math, right? And most of you at this tutorial should be familiar with what an XOR is, but essentially it's much simpler than a subtraction. So at each step, normally we would just put two numbers and subtract them and you get the next level. Here, what happens is that when you divide, you're just going to put the polynomial and do a subtraction using XOR, which is the same as an addition, subtraction, all those are the same in Galois fields. So you would get this very simple. So 1 and 1 is 0, so something like that. So you will end up doing those operations over the whole length of the message, right? If the message is going to be k bits, then basically this division will go on for all of k bits, and then once it's done, what you have left over is going to be your CRC, or the remainder. So that's the general high level view of this. Now, the principles of acceleration, and I've showed this in multiple of my videos. There are two main principles of doing the CRC fast. Now, I'm going to follow this this is mostly when we look at it from a table perspective. In a table, we have to accelerate the function so that we can store functions for all the bytes of the word that we are dealing with. Now, we could be dealing with, like in my case, I usually deal with 256 bits of data. It could be 512 depending on what speeds you're operating your hardware at. But let's say it's 256 bits, which is equal to 32 bytes, right? So given 32 bytes is what I'm working with. Now, if my message is just 32 bytes for that clock cycle, each byte is treated as, one part of this whole message, right? So, and I'll show you this in a second, but you have to consider the whole 256 bit. So this would be written as 256 bits. The next one, the next one, the next one, all of them would be written as 256 bits words. And then we would basically sum them up, each byte lane, and then we would make the whole word. And then the math of this works out that CRC of this summed up function or the whole word is CRC computed over each word and summed up, right? So there is this underlying function that we will use for our table generation. The other is that if a byte is followed by a bunch of zeros, let's say k zeros to be precise, then basically that is going to be the CRC of that value evolved, which is like CRC computed by pushing in k zeros, right? This is like if k zeros were pushed in behind that byte, what would happen is defined by this second equation. So given that you have 256-bit word, let's say your word is a very large long word, so you break it into bytes, or even bigger, let's say 4 bytes or whatever. You'll see different approaches being used. In my case, I prefer bytes because tables are easy to make over bytes, right? Because each table is 256 deep and not like gigantic. So that's what I do. Now it's a sum. Let's say this was A1x, this byte was A2x, and so on till like ANX. These are what is shown here. And then the other thing you would do is that this is not just A1x, this is not just this byte, this is this byte followed by so many zeros, right? So if this is 32, then this A1x would be followed by 31 times 8 zeros, right? So that is what you have to understand, is that when we are summing them, we are summing them with the whole word, right? So that's one. The other is that because we have 31 times 8 of zeros behind it, then we will apply this, and we call this step evolution. We call just a byte being computed as CRC computation, and this is like evolving it, right? Which is if you just push in zeros behind it, not in front of it. Front zeros don't really matter, right? If there were zeros in front here, they don't matter. It's the zeros behind that are useful and critical. And so we will evolve CRC using that this second equation, right? So that's, remember these two equations, you can come back to them, but this is very important to understand. You might want to take a moment and make sure you understand these two principles, because all of the CRC acceleration theory is based on these two principles. Okay, now a quick word on, like, some of you might be interested in thinking about this efficiency of CRC itself. So the CRC theory is based on what we call as the Hamming distance. So picking a CRC equation and its efficiency depends on when you code a message with its CRC added, then what is the Hamming distance between code points, right? So you can see that for this traditional IEEE CRC, if you have, and it's coded here, Hamming distance is given for a message length, right? So the message length here is 8 to 10 bytes, all the way up to like, very large, huge message lengths, right? So normally Ethernet frames may lie like 1500 bytes. So maybe they will lie here, because this goes all the way up to 3000 bytes. Right, so the Hamming distance here is 5, right? So different CRCs have different Hamming distance, and so when people work on picking CRCs, I think there could be a lot of work done to prove what kind of CRC functions or polynomials they would use. But suffice it to say, it doesn't matter which polynomial you ended up picking. whether it's this polynomial, this one, whatever polynomial you ended up picking, the theory works exactly the same on all of them. So once you understand this theory, you can apply and change it to whatever polynomial you have picked. Okay. Now, for the CRC theory, the CRC is seen as an LFSR. So when the data bits come in, right, the data bit is XORed with the CRC state bit 31. And so remember, the two critical items is DIN, right, and CRC bit 31, right? These two in any given step, these two are the uh, you know most valuable players. Most valuable players at any given step are DIN and CRC31. And so when we sum up, when we do the breakdown of the table, remember that these would be the most important. When you think logically about them, you will focus on DIN and CRC bit 31, the state bit 31. Or if you're computing CRC64, it'd be the same thing. It'd be CRC bit 63 and your DIN. Those would be the key things. So accordingly, this theory will always hold, right? So if you are using this kind of LFSR, make sure that this is the kind of LFSR, because they come in two different formats. So for our case, we are using this LFSR, and the data in and the CRC bit 31 are what are used to compute CRC at every step. And all the theory will be based on the fact that we are rolling this LFSR function to many bits, 256 bits in my case, but you could make it to however many bits you want. Okay. Now I'm going to describe now how people who use functions to do CRCs, how that works, right? So now that we have seen how our LFSR works, if you go to these websites, there are multiple websites that do this. This is one of the websites, buse.ch, and you can see that they have the CRC HDL code generator. This gives you the hardware description language, either Verilog or VHDL, and yeah, and or MyHDL too. Wow, this is great. They also do MyHDL. This is fantastic. I love MyHDL because this is Python based, and I do a lot of work in MyHDL. You can check out my channel about that. But so here we picked up the standard CRC algorithm, and this is the polynomial, right? The division by this polynomial to do the remainder. And so this will tell you, oh, I want to feed in 32 bits at a time or 64 bits at a time. I think this goes to a max of 64. So if you want to go higher than that, you would have to probably find some other way, maybe use ChatGPT or something. You can probably figure out a way to unroll the equation or roll the equation, but for 64 bits, right? So if we just use 64 bits of input word, then it'll unroll it. And so you can see that CRC0, right? Here you can see CRC0, bit 0 of CRC is computed at every clock cycle, assuming 64 bits of data have come in. It'll give you this equation. Now, the question is, when people start doing this in high-speed logic, and you want to say, okay, I did it 125 megahertz, right? Worked out fine. I could close timing. How about 250 megahertz? How about 500 megahertz? How about 800 megahertz, right? So the question is, for hardware designers, it's always a challenge. It's like, what speed do you want to close timing at? So we are going to discuss like how should you think about these functions so that you can improve the speed of a function based, right? This is not table based yet, but this is a function based. You can go on the web or download some software that will give you, the unrolled CRC for your data width, right? So that is what we're going to talk about next here. So think about when you got your function has, bits from bit 63 down to bit 0, right? So you have all the bits of data and you have CRC bits. So CRC31 down to CRC0, right? So any output state, let's say CRC0, like if you go back here, you see CRC0 is being talked about here. So if you look at that CRC0, you know that it's made up of bunch of CRC bits and bunch of data bits. Now, the way to think about it is you can split these functions, right? Because it's at the end, it's just an XOR. So you can XOR in chunks, right? You don't have to XOR all of them. So you can XOR data itself, right, at that step. So you can, in this case, instead of lookup table, you can just use XORs, right? So you can XOR these chunks of data. Let's say I want to do, let's say this is 256, so I want to do 64 here, next 64, next 64, next 64. So I can write down my function so that I do XOR of any 64 sets, and then I flop it to improve my timing. And then once I have 4 of those, I take 4 of those bits and I XOR one more time and I flop it one more time, and there you go. I have a very nice timing that might go to 800 megahertz. And then parallel to this, I also know that I have some bits from CRC31 down to 0. So I will, because I'm not using 2 levels, so I'll just put delay flops here, right? And then two delay flops, and then I will put my XOR here. Instead of lookup table, I'll do my XOR. And so this will be at the same time as the one coming from the data. And once I XOR those two and I flop, that is my CRC output. So this is CRC out. So then I feed it back in for the next clock cycle, and this goes on and on and on. So this approach, this is also known as the pipelined CRC approach, and you will see this approach used everywhere. Whether I use tables, whether I use functions, it doesn't matter. The question is that the approach in functions is that I take a large function from wherever I got it, from views.ch or wherever, ChatGPT, whatnot. But then I'll take each bit and I'll break it down into sets, and I'll XOR in this fashion. I'll XOR the CRC bits by themselves. I XOR the data bits in these sets, and I do all this pipelining. As I've showed you, you do this pipelining and you will improve your speed significantly, right? And you can make more pipelines. You can make any number of pipelines. You can make n stages of pipelines here. Remember that you can always pipeline more. And so that is the trick or technique. I could have 10 stages of pipeline here. It doesn't matter. So fundamentally, I have taken a function that I got, and then I built this. Now, keep also in mind that the tricky part in CRC is the last clock cycle, because in the last clock cycle, you do not have the full word. You have less bytes in the word. So in the last clock cycle, you could have 1 valid byte, 2 valid bytes, 3 valid bytes. So how you deal with that is a whole other thing, but you can apply similar principles. You may have to mux the possibilities, whatever happens, right? So given the last clock cycle, you could have many functions, and you'd have to mux the right values, but each value could be computed in this fashion, right? So CRC at very high speeds is complicated, but this is the approach you use for generating function-based CRC at high speeds, like very high speeds. You could build an extremely high speed CRC function using this technique, right? You don't have to do any more fancy math. The fancy math is fairly straightforward once you understand this. So now let's look at CRC tables. Now table-based CRC is going to be a little bit similar, but I'm going to teach you one basic technique to look at CRC. When you think about tables, you have to think about one special way. You have to think of each bit as like people entering a store. So one bit of data goes in, and then it does some work, and then it's done. And then the next bit goes in, it does something in the store, and it's done. So I'm going to show you what the CRC looks like. So there are two separate things. There is the CRC bits 31 down to 0, and then there is data bits, and data could be any number of bits. In this case, I'm showing 63 down to 0. So there is data bits and the CRC bits. Now keep in mind that every single bit will have a CRC state behind it. When I showed you that CRC of A of x is sigma of CRC of AIX, where the sum of parts, so CRC of sum is sum of CRC of parts. So this first equation that I taught you earlier, this, what it really means is that each bit of CRC has a CRC behind it. So there are 32 bits of CRC state behind it, 32 bits of CRC state behind it, and 32 bits of CRC state behind it. So there is 32 bits of CRC behind every bit of CRC, and there is 32 bits of CRC behind every data bit. All 64 bits will have a data bit. So this is the general idea. Once you grasp this, then you start understanding what table-based CRC really means here, right? And the other thing is that I mean, one could, this is the simplest form of understanding the CRC tables, but I don't do it on a bit basis. I do it on a byte basis because tables can easily handle 8 bits. So what I will do is I'll combine 8 of these bits into one byte, right? So a CRC state would be just, 4 CRC states. I will use the 4 bytes of CRC32, right? So the byte would be, byte 3, 2, 1, and 0. And likewise, the data, I would also treat it as bytes. So byte 7, 6, so on, so on, so on, down to 0, right? In this case, because my 64-bit word, I'm going to treat it like that. So this is one simplification, but really what I want to tell you is behind each of these is a 32-bit state, each of these. And when you sum up all those states, then you get the final CRC, right? So each of these carries a 32-bit state, 32-bit state, 32-bit state. And we are going to evolve each one of them and sum them up to create the state of the table, okay? So in a way, it's kind of like the Fourier transform, right? Because you have to understand each component, right? So when you say CRC, you're not just computing CRC. What you are doing is that you understand every component of the CRC. So CRC has two components. One is your CRC state, which has 4. In CRC32's case, you have CRC consisting of 4 bytes of CRC state and 8 bytes of the data state, which is, your data byte 7, data byte 6, data byte all the way down to data byte 0, right? And there is a CRC32 behind each one of them, right? Because you have to see if that was the only thing you were dealing with, and the table just evolves these. The table will evolve just by looking at 1 byte. It doesn't even know these exist. So likewise, when you look at this one, it doesn't even know these exist. So therefore, the tables think of each component. It's like a Fourier transform. Each of these components is seen in isolation. And then at the end of it, you just sum all of them. You take an integral over all of those components. A sum over all those components gives you the final CRC of that clock cycle. And that is the beautiful part of CRC tables, is that once you get this, it's like, it's an aha moment that, okay, now I understand why CRCs work the way they do. Because at the end of it, it's just a remainder, right? But the remainder is done so that the message that I'm computing over, right? In the dividing is by always the same polynomial, but the message can be broken into its individual components, right? This first equation, A of x, is a sum of parts, right? The whole is a sum of parts. And so I just break it down into parts, and each part is seen in isolation, and a table evolves that. And that's how we get to the final CRC. Okay, so next, it's the same function here. So here, what we have done is that instead of XOR functions that we saw, we have now lookup tables. And these lookup tables know exactly, this is not the same lookup table, because for byte 0, I know that this byte is not having zeros after it. This is the last byte. So there is no zeros following it. There's nothing following it, right? If this is byte 1, then we know that there's 8 bits of 0 behind it, right? So 8 bits of 0 behind it, and next it would be 16 bits of 0 behind it, and so on. So there is this evolution, evolution using how many zeros are following it in that given word, right? So that is what these lookup tables would have. This lookup table would be 0, this lookup table would be 8, this lookup table would be 16, and so on till you reach the byte k. The kth byte will have, k minus 1 um, times 8 zeros behind it, right? We know that. So I think that is the first thing. So lookup table design, and we'll look at the code next following, so we can see how this code is generated, but it's very similar. For each data component, there are k bytes in the word, and so each data, this is the data component, right? Just like I said, this is like the Fourier transform. There is a CRC component and there is the data component. So the data component is seen as, you'd have all these data bytes, and then on the other side, you have the CRC component. And this is the CRC component where you have 4 bytes of CRC, the upper byte 3, 2, 1, and 0 for CRC32. And so you'd have those 4 bytes here. And each of these 4 bytes would have its own lookup table. So there'd be 4 lookup tables here, right? Each would be, so this would accordingly would have, how many, this is k minus 1, this is k minus 2, and so on. However many zeros are following, you would basically be evolving the function by those many. And I think that in this case, it'd be k. So accordingly, you would basically write up the lookup table functions for these, right? So CRC works very much like function. Now, if you find it easier, at this point I would stop and say, if you don't understand table-based approach, if it's getting harder for you to understand, then I would say stay with the function-based approach, because it's so much easier. You know already the functions, you divide them up into different sets, and then you do the pipelining, right? It's very, very simple. Tables are a little bit more complicated, but it is also simple to understand once you grasp it. It's very similar. If you have the memories available to you, table-based approach, so much faster, because there is no timing to meet. It's just a lookup table. It's constant time to look up, right? Whereas XOR functions would be like, okay, how big the XOR is and so on. You'd be tuning it and so on and so forth. So accordingly, you can see that this is just a memory lookup, right? It's always fixed speed. When 1 byte goes in, it'll produce a fixed speed here. So this is one way, right? And then on the CRC side, it's very similar. You have 4 different bytes of CRC coming in, 4 different lookup tables here, and they are a fixed offset, because when the whole k bytes go in, then this topmost byte would evolve by k, the next one would evolve, so this one would evolve by k, right? This next byte would evolve by k minus 1 bytes, this would evolve by k minus 2, and this would evolve by k minus 3, right? Likewise, this byte k would itself evolve by k, and so on. This would evolve by k minus 1, and so on, so on, and so forth, right? So for most part, this is true, except there's going to be one quick thing. In the last clock cycle, it's not going to work like that, because there's all these words are full words. Last clock cycle is different, because the last clock cycle has different number of bytes. Now I'm going to say the CRC part is what I'm going to show. So one quick word on CRC is like, if the last clock cycle only has 1 byte, right? If it only has 1 byte, then you know that the topmost byte of CRC will evolve by 1 byte. But the lower bytes, because they will not even reach the top, right? They will not reach, I told you at the beginning, the MVP position, which is like when you reach the LFSR's topmost position. If you don't reach that, then you just left shift, right? So you will left shift, So however many bytes there are, you will just left shift by those many bytes. And that's all that'll happen. Once you reach the topmost position, then you start evolving, right? So any bytes that you have after that point, you'll start evolving. But before that byte comes in and reaches the MSB, you are just left shifting. So if there's only 1 byte, everything left shifts by 1 byte, right? 1 byte, 1 byte, 1 byte. And if there were two bytes, then everything would shift by 2 bytes, and this would actually evolve. So this would evolve by 2 bytes, and this actually would evolve by 1 byte because it would have already reached the top. And then this would evolve, this would left shift by 2 bytes, right? And this would left shift by 2 bytes, and so on and so forth. So you have to keep that in mind, that once you get to the last clock cycle, the last clock cycle is a little bit more complicated. And in that case, the data still follows the same pattern. The data would be like, if there's only 1 byte, you would just load that byte in byte 0, right? If there were 2 bytes valid, you would load them accordingly in byte 1 and byte 0, and so on and so forth. So last clock cycle still for data can be loaded still in these registers, right? But CRC, if there is enough bytes, if there is more than 4 bytes, equal to or more than 4 bytes, then CRC can also be loaded just like data, right? Because each of these evolves exactly by that amount. But if there's less than 4 bytes, then you basically have to right shift, and then so not everything evolves, so that you cannot use lookup tables, right? You see that you only use lookup tables if the last clock cycle has 4 bytes or more. Then everything gets a lookup table. If only 1 byte, then only one of these highest MSB gets a lookup table. Everything else gets a shift by 1. If there is 2 bytes, this gets a lookup table, this gets a lookup table, and these two are just shifts, and so on and so forth. So hopefully you got that, and then you XOR and keep going the same way. That's just like our previous cycle, right? So you do this. Okay. So now I'm going to look at the code, right? So since we have already understood the table-based approach, and table-based approach is fairly simple once you understand that CRC is really a sum of parts. CRC, right? It's a sum of parts. Excuse me. Or integral taken over CRC of the parts. So let's look at the first thing, that how do we create these tables? So table is really based on very simple approach. This is something that you would have already probably seen many times. Even software developers use these tables. These are just tables that are, I guess, for 8-bit words, right? So if you're given 8-bit words and a poly, right? Given a poly and 8-bit words, you basically create its contribution, right? Again, I said you have to think of this word in isolation, right? What would this word in isolation, if this was the only word in the message, what would it do? And so the CRC basically just computes, if I was to squeeze in starting with a original value of 0, right? So original CRC has to be 0. And given that the CRC is 0, what would the value be of CRC at the end of it, right? So that's what, and this is CRC32. So we are assuming standard Ethernet CRC, and the poly is, you can check the poly here, right? You can check the poly here. I'm using standard Ethernet CRC poly, and so like I said, the most valuable thing is the uppermost bit. This checks that the uppermost bit of the word is 1. If it's 1, then we XOR with polynomial. We left shift the value by 1, and then we XOR with polynomial, and we take the value. We take the lower 32 bits of that value. So the upper bit is thrown away, right? Once it's checked, you check that bit, throw it away, XOR with poly, and take the lower 32 bits. That's it. If that bit is 0, then you just throw away. You don't XOR with poly, right? You just throw it away. And this is very reminiscent of a division algorithm. So you can go back and check. This is exactly how the division algorithm works. And so this is what this does, right? It's equivalent of a division algorithm, except it is in Galois field of 2. So instead of doing a subtraction, we do what is called as an XOR, right? So it's a division by using XOR, Okay, so that is how we compute our basic table. Now keep in mind, we have talked about two separate things. Because we are not doing this in software, we are not taking each byte as a byte, right? There is another trick that we have to do, and that is called zero extended tables, right? Which means that when we take a table that has this base table, what we are calling here is the base table, right? We will extend these tables to have certain number of zeros behind them. So like if you take a word, right? If you take a word and this MSB is some byte, right? Let's say some byte, right? Value V. But in that word, you know that behind that byte V, there's also place value, right? So it's got zeros behind it. So we have, and those zeros, as they get pushed in, the state of this byte CRC, right? There is behind this byte is also CRC32. I showed you when we did the Fourier transform kind of thing that, you know, when you do, each byte has a CRC associated in isolation. So when other zeros are pushed in, each CRC evolves, right? So when zeros are pushed behind you, not in front of you, in front zeros don't matter. If there's zero in front of you, they don't matter. Your CRC state will not change till you reach the top. When you reach the top, at that point, when you impact the CRC register, your CRC state starts ticking, then zeros behind it will tick you up, will keep ticking you, right? So that's what will happen here. So we will zero extend, and the zero extend table in our case, we will create a table of tables, right? So we will start with the base table, which is, you know, by evolved by zero. So this is evolve by zero zeros behind it, right? And then in this case, we are going to just look at, you know, how many zeros we need. And so we will go ahead and create those tables, right? So, so zero extended tables, the way they are created is that you will start with the base table, and then once you take in all those tables, what you will do is that you will push in. So right, so you can look at this, that the way it evolves is by using this equation. So you take the uppermost byte, and then you basically take the value of CRC, right? And then you let me see this. Okay, so okay, yep. So what happens is that, so now think of it, when you are given, this is like evolving a CRC, and I'll show you quickly how CRC evolves. So when you pass in, let's say, some number of zeros, right? Let's say 8 bits of zeros. So what will happen is that 8 bits of zeros will only impact this topmost word. The rest of them will just shift up. Everything else will shift up by 1 byte. But this would actually evolve, right? And by evolve, it's like, you know, CRC lookup. So what happens here is that we first compute the uppermost byte, right? Because that's the one that will evolve. And so we basically look it up in the base table, which is base table evolves the byte, right? And so we look it up in the base table, and then the lower bytes, these bytes, because they have still not reached the most valuable player position here at the top, they're just shifting left. They're just shifting left. So you can see that everything else is just shifting left. The 24 bits of lower CRC are just shifting left. The uppermost is evolving, right? So this is evolving. These are just shifting left. So the next table is evolved by shifting left of everything by 8 bits. And so we kind of cascade this. So base tables, everything was some value. Now we take these values and pass in one more set of zeros, we get state 1, right? Which is table followed by one byte of zeros, right? We take this table and pass another byte of zeros, we get 2, right? So we get 2, and then so on and so on. So in fact, this is a very nice way of doing it, because instead of computing it again, this is kind of like what do you call it? Like a dynamic programming way of doing this. This is very, very nice. It's a very you know, elegant algorithm because we're taking the base table, which is just the byte itself. We evolve by 1 0 and we get this table. Now we use this table, right? Because it uses z minus 1. So every stage uses the tables from the previous stage, and all it has to do is push one more 0 because previous one already has 1 0. So if I want to get 2 zeros, I'll take 1 zeros and push another 0 and so on. So it's the same algorithm repeating over and over and over. And this is really elegant. I like it. This is really a very beautiful way of developing these tables, right? Next up, so once we have these tables, right, these evolved tables, then we have to, the next step is to actually, yeah. So the next thing is that we will take these tables and create all the tables, right? Those were the subroutines. Now we are actually using them to create zero extended tables, right? And we only have 32, up to 32 bytes of zeros, right? Because our word is only 256 bits, right? So 256 bits is only 32 bytes of zeros. But I have created some more here. So I've created a table which goes all the way up to 40. I don't really need this. I think 32 would have been sufficient. So I really needed this number to be 32 here, right? I don't know. I think I'm just being overly cautious here, but it's not really needed. I need 32. So now I'm ready to compute my parallel CRC using this function. And so I'll initialize my state, right? And then I'll basically start iterating over my data. My data is my total message, right? My message may be a very long message. I'll break it into, 32 byte chunks, my 256 bit chunks, right? So I'll chunk my data so I can feed it into my CRC machine, right? And in the end, I know I may not have full word, right? This may be 32 bytes, 32 bytes, and 32 bytes, and so on. And then some leftover are remnant bytes, right? So something like that. Now, so this loop keeps going. Most of these loops assumes that you still have 32 bytes remaining. So if the remaining bytes is greater than 32, then that's good. If the remainder bytes is less than 32, then that means you're on the last clock cycle and you will use a different algorithm. So if it's not the last clock cycle, like I've showed you, that you'll figure out the state bytes first, right? And then once you have the state bytes will evolve, and the state bytes will evolve. So the first byte, right, the state bytes would evolve by a certain amount. So first byte would evolve by 31, right? And then next by 30 bytes, next by 29, and next by 28 bytes. Okay, and I want to say a quick word here, right? Because really, it's not 31. This is actually 32. And I want to say this, when we created our base, remember when we built our tables, we did table and then b plus 1, base table, and b plus 1, then b plus 2. That is push 1 byte of zeros, push 2 bytes of zeros, and so on. Remember, this base table assumes that you are processing the first byte, right? So when you push in a 32 byte word, the base table already assumes that 1 byte is being processed. So when I do 31, that means the base byte plus 31 zeros, right? So that's what it means, right? So keep that in mind, that this really means you've evolved 32 times. That's how the tables are constructed, right? So keep that in mind, that it's assuming that you get once you start with a CRC state, you're really getting 32 bytes of zeros. So that is that is what this one is. And then then you do this basically over all four, because this is very consistent. This is always, once you get, except for the last clock cycle, every clock cycle is going to be the same. You just get the same 31, 30, 29, 28. You just keep getting this again and again and again and again. You just keep getting it. Last clock cycle is going to be different, because this may only evolve by 1 or 2 or 3 or whatever, how many bytes there are. It's going to evolve by that many. And the others will just shift. Sometimes shift, sometimes they will evolve. So last clock cycle is tricky. We'll look at that in a second. For data is the same thing, right? Because you take a look at the data and then you evolve it by the same amount, right? Because the highest MSB of data will evolve by, 31, same thing. And then so on and so on and so on until the lowest byte, will evolve by 0, right? It'll just be, it's lookup, right? Just lookup, no more zeros. So 0 means just a lookup, which still means that all 8 bytes get used up, right? But its 8 bytes get used up, right? Its 8 bytes, whatever is in the register, its 8 bytes get used up, followed by just zeros getting pushed in, right? So the point is that, this evolution function applies only on the first n words, not the last clock cycle, because it's very consistent. CRC evolves by this function and data evolves by these functions. It's very, very consistent. So you just keep doing that. And then keep this in mind. This is your integral function, right? Or your sigma function, where we said CRC at the end is basically sum of CRC. So when I do this for loop, this is also that sigma, right? So you can see, or integral, you can see that these two equations are summing over all possible components of this. It's like a Fourier transform. You have to sum up every byte of the CRC state and every byte of the data state, right? You have to evolve every single byte by every possible bit that has come in, and then you sum them up, and that's how you get to the final. This is the magic of CRC. Once you understand this, then you understand that the sum of parts is basically exactly equal to the CRC at the end of it, right? And so you just keep going through this. And then in the last clock cycle, it's a little bit different. Now in the last clock cycle, you again have the different state bytes of the CRC. But when you load the CRC, you load it on the right side, right? So you load it, you load the tables on the right side. And the way I have set up my tables is that these tables will go, down to 0. And when you go negative, -1, -2, -3, if you load these, the lookup tables will just shift the data. That's how I've set up my tables. The lookup tables will just shift the data if you're negative. If you're 0, it will evolve. If you're 1, it will evolve, so on and so forth. But if you're negative, so we just basically look up. So we load the CRC in the right location. And if there's only 1 byte, then the 3 bytes of CRC will just shift left and the 1 byte will evolve. So I have done these tables intelligently on the negative side. And the same thing happens here, except data will never go negative. Data will only fill on this side. So we'll align the data here, and then we'll do the lookup. And then the CRC again in this last clock cycle, same thing. It's the integral, and then this is basically, this is the integral, and then at the end you basically just make sure you only take 32 bits, so you remove any higher bits, right? And then finally you just output or print the CRC. That is the CRC calculation, right? So that is it, guys. So you can see that there are 3 main ideas of CRC, right? First was the CRC of a sum AIX, right, is equal to sum of CRC of AIX, right? This was the first formula. The second was that, if you think of a word of CRC, right? If the CRC of something like a byte followed by x to the power k, right? If there are k bits of zeros following, then you basically take the CRC of the byte and then evolve it. So then we have taken, see that we took a table of that CRC, right? And we evolved it by pushing in, n or k bytes of zeros. So this is the other thing that we did special. The third thing that we did was we also were aware that in the last clock cycle, CRC evolves by the number of bytes that are there. So you can end up with some bytes of CRC, like the lower bytes of CRC state evolve by, just shift. They don't really have a lookup, they're just shifting. And this happens because they haven't yet reached the top level. The CRC only evolves if you have reached the top level. That means if you have not reached the top level, you're just shifting left, right? And so this can happen in the last clock cycle only for CRC bytes. It does not happen for data bytes because by definition, every data byte has to go all the way and it has to be passed. Remember the polynomial that we saw, that we showed you that, the DIN and CRC31 and DIN, they have to XOR. So this has to happen for every data bit, right? It doesn't happen to every CRC bit, but every data bit. So in the last clock cycle, if you only have 1 byte, then each bit of that data has to go all the way to the top. But some of the CRCs may not reach there. So in the last clock cycle, we have this extra provision of handling a shift for CRC. And so these were the three main principles by which the CRC was organized. We also showed a way of pipelining. So we showed you how to pipeline the CRC and data. So you had data, you had different stages of XORing, and then eventually you merged all these and then you feed it back onto the CRC. So we showed how to pipeline these efficiently. We showed this on both functions and tables, right? Because you can do this using functions that are available online, and you can do this using tables that I have showed you how to build. And you can go through them and you can ask me questions. If something is not clear, you can ask me questions. I'm happy to provide you my code if you want to try it. If you want to go through my code and understand it, I'm very happy to provide you the Python code. You can run it yourself and see how it works. You can learn it. You can ask me questions. No problem. I'm very happy to help you. But hopefully you enjoyed this, and hopefully you understand how the math behind CRC works. It's just a remainder math, but at the same time, once you understand that it's kind of behaving like a Fourier transform, it's behaving like a sum of parts that behave and evolve individually, each component, and that each leads to a final summation into the CRC at every step. Once you understand that, and once you understand how the evolution functions take place, like if you have a CRC followed by, k bits of zeros, then it means that you first compute the CRC over the byte that is there, and then you evolve by pushing in zeros into it, right? So that's what we do. And so those functions are available to you in my code. Take a look at the code, and then hopefully, this helps you. If it really did help you, give me a thumbs up, and subscribe to my channel if you have not, because this really helps me. If you guys found any value out of this video, if it helped you in any possible way, set you in the right direction, helps you get to your code done, and helps you achieve speed, then do leave me a comment. If this helped you in any way to improve the speed of your verilog VHDL code for your ASIC, FPGA, what have you, then do reach out to me and let me know how it helped you. If you have questions, feel free to ask me. Otherwise, I'll catch you in another video. Until then, take care and bye-bye.